So again, I just drew a nice bold-faced line where the zeros are to try and exaggerate that's 0 meters per second. And from here, what we're asking you to do is I think pretty easy. I want you to create a position versus time graph. Be intentional. So make sure your position versus time graph has all the qualities we talked about last week when we did this. So I want to walk around in the first 5 minutes or so and see that you got number 1 done. Over here. So let's talk about the first one and what my expectations would be. And there are several things here that may seem subtle, but if you're hoping to get a perfect on your first pop quiz, you might want to make sure you have these written down. The first thing I want to say is, do you notice that this graph has kind of got 3 sections to it? So when I see this graph and I'm trying to make a determination as to what's going on here, the fact that there are 3 sections is important. Not all graphs are going to have sections, but many do. And they're not always as obvious as this one. But this one's pretty obvious because I see abrupt changes in the object's velocity. I'm looking at time equals 0 and noticing that we are observing the object over the span of 10 seconds, which means your position graph will also be an observation of the object over a series of 10 seconds. So the first thing you could do just to get started is to identify that the horizontal axis, 2, 4, 6, 8, 10, is going to be 10 seconds. I'm going to point out that even here, I do make mistakes. I want to try and use up as much of the graph as possible. Often a point is issued on the AP exam for using more than 50% of the provided space. If you didn't use 50% of the provided space, you wouldn't earn that point. So I would encourage you to use the space provided. You'll notice I'm labeling it because you will always be given points for correct labeling of an axis. And I'm putting position here. That statement, that tells me where the first dot's going to be placed. It says that at time equals 0, the object is at the origin. So at time equals 0, the object is at the origin. So all of you who started your dot somewhere else, they're all wrong. And that's a pretty big group. All right. This is a velocity graph. Its area tells me the displacement. Area is the portion of the graph bounded by the curve and the axis. We reasoned our way through it as well. So some of you could reason your way through, and that's fine. But I would encourage you to get away from just reasoning here. There's going to be cases coming up where reasoning won't work. But you could reason this one. The object traveled 2 meters per second for 4 seconds. Well, if it's traveling 2 meters each second, and it does that 4 seconds in a row, it's going to move 8 meters. Now, that part's pretty easy, but that's something you can do because the velocity is staying the same the whole time. When the velocity is no longer staying the same, that's going to be a difficult argument to make, which is why I need you to transition to having a more robust understanding. But can't force you. All I can do is tell you that I'm doing the same thing by finding this area. You remember doing this last week? Hope so. All right, so that means this section had a displacement of positive 8 meters. Like I said, I'm going to go as far as to even put the positive there, because this is velocity. Velocity has direction. And so I'm making sure in my head I know the direction is positive. It's moving in a positive direction. There's another section here, though, so I'm going to take a look at the other section. That's here. It has a width of 4 seconds as well, but it has a length of -1 meter per second. So in trying to figure out the displacement over this interval, -1 times 4 is going to be -4 meters. So it seems to me that I have 3 sections. Now, I only talked about 2 sections. I didn't talk about this section. Why didn't I talk about this section? What's that? You're fine. Go ahead.
0.
What's at 0? the velocity is 0, which means it's not moving. Or the first 2 seconds, it just stays there. It has no velocity. So this ultimately is 0 displacement. All right, displacement is change in position. My object traveled 8 meters forwards and 4 meters backwards. I need to identify an appropriate number line in the vertical direction that can accommodate the motion of this object. Since it goes 8 meters forwards and then 4 meters backwards, it never gets further away than 8 meters from the starting line. So I'm going to have 1, 2, 3, 4, 5, 6, 7, 8 meters along my number line here. I've accommodated the motion of the object. All right, in the first 2 seconds, the object doesn't move. That means that my next dot's going to be there. In the next 4 seconds, it moves forwards 8 meters. So I know that at 6 seconds, it's 8 meters away from the origin. So I'm going to put a dot right here. Try to line it up with the 8 meter mark and line it up with the 6 meter mark. Now, I have to connect those 2 dots together. This is not done in an arbitrary manner. It has to be done intentionally, which is why I suggested you take a meter stick out, or I'm sorry, a meter stick might be a little big, a ruler, straight edge, driver's license apparently works. I even saw credit cards last class period, but you won't be able to take those out in the AP exam. Get yourself a small ruler and intentionally draw a straight line between those two. The reason I say the word intentional is because they are looking to see if you understand that the velocity was a constant. If you hand draw that in, they might interpret that as being curved. You need to be intentional. From here, it moves backwards 4 meters. So that's going to take it from 8 to 4. So 7, 6, 5, 4. This is right there. Something like that. And again, that was done in a constant way. So I will try and be intentional about it as well. This is what the graph should have looked like. Now, I had about 60% of you who were really close to this. Look great. But I'll point out all the things I am looking for. Clear articulation of where the points are of its motion. So, these data points, that needs to be clear. An appropriate use of the axes, using as much of the graph as possible. Labels on the axes that indicate the units from your measurement. A reflection of the starting line being where you're told to place it, and an understanding that you can't get that from the velocity graph. And then intentional use of straight lines to indicate constant slopes. Those are things I will be grading. So, based on my cursory walk around the room, like I said, 40% of you couldn't do this, with some of you not getting anything down on the paper before I actually came by the second time. So I think that this should be enough. If this is not enough for you, I will post practice tonight, so you should practice. But you should demonstrate that that was enough, and now you have this one completed. So I'll give you another minute or two. I want you to complete this one. I really want to do this one. But I think I'll need to probably make sure that I've captured those 40% of you who haven't acclimated yet. Although this was stated, it gets more and more confusing as your graphs get more complicated. Area is between the curve and wherever 0 is. So when you're looking here to figure out how to deal with area should stop at 0. That's why I drew that big bold line in and recommended you did the same, because a lot of people will carry this down to here, or worse, will carry it all the way down to where the bottom of the graph is, and that's not okay. So that's an area, that's an area, that's an area, those are areas. It's bounded between the curve and 0. Perhaps I can go through this a little bit more quickly. Let me start with, I see 3 different areas. Do you see 3 different areas? So area number 1, area number 2, and area number 3. And length times width, 5 times 4, positive 20 meters here. Questions about that? All right. Negative 1 times 5 tells me negative 5 meters here. Everybody okay with that? And then it looks like negative 3 times 1, negative 3 meters here. How's that? Any questions about where I got any of those? So I went forwards 20 meters, backwards 5 meters, and then backwards 3 meters. So it looks like I started at 0, and I'm ending at 12 meters. All right, so let's see what that looks like over here. First reminder is that we can't get the starting position from the velocity graph. We have to be told the starting position from something else. And again, we were told at the very beginning to start at the origin, so my first dot's at the origin. In the first 4 seconds, I moved 20 meters. So I've already got my 20 meters here. That puts a dot there. The velocity was a flat line, which means the velocity was constant. So I need my slope here to be intentionally constant. Now, over the next 5 seconds, the object slowly goes back 1 meter. Slowly goes back 5 meters. So I'm at 20, 18, 16, 15. So 15 is like right here. So something like that. Now, in the next 1 second, I jump back 3 meters. So I'm at 15, I want to drop to 12. So let's see, 2, 4, 6, 8, 10, 12, something like that. And again, intentional. My graph should look something like this. On graph paper, I'd expect it to probably be a little bit more exact, but notebook paper like this, you should be as close as you can make it. Reasonable. Questions? Yes, sir?
So do we only need the max number on the vertical axis?
You need enough to accommodate the motion of the object. So max is probably the right word there, but I don't want to say it that way because you can have any number of other changes. We haven't really seen one that does that. Now, I think that this is kind of basic. This isn't the level at which I'd like us to be working. The level I'd like us to be working are these down here. Hold on. The level I'd like to be working is these like this. I want to work one like this. There's something different here, and I hope you know what is different here. Now, how we deal with this, that's going to be a whole nother thing, but there's something very different here. This object does not have a constant velocity. This object's velocity is constantly changing. It starts from rest, and by the end of our interval of 10 seconds, it's traveling 20 meters per second. So I know just by looking at this graph that my position graph is going to be starkly different. The position graphs we've had before have always assumed that the object had a constant velocity, and this is an indication that the velocity is constantly changing. But all the rules, the velocity graph doesn't tell me where I start. The start of the problem told me to use the origin as my position. That's still true. Next, the area under the curve is what's going to give me the displacement, the change in position. I'm still going to do that here. I'll point out that 0 is right there. So if I want to intentionally indicate that this is the 0 axis, I can. But my area will now be here. Well, luckily, I've had a course in geometry, and I'm pretty sure you guys remember how to calculate the area of a triangle. So 1/2 base times height work for you guys? So I'm going to do the same thing, 1/2 the base is 10 seconds, and the height is 20 meters per second. I'm still doing just area, nothing fancy. But I will point out that this gives me a displacement of 100 meters. And it's positive. So there's only one section to my graph. So I've got the section now. I'm going to go over to the other side here and begin my position versus time graph. And you're going to be frustrated perhaps with me, but I'm short on time. But I don't have to worry about other middle sections or any middle pieces. I know where it starts and I know where it ends, and that's it. So and now I have to connect these. And herein lies the difficulty. When I go to connect these two dots, I have to remember that the velocity starts at 0 and ends at 20. So that means, and I'll translate it for you, the slope starts at 0 and ends at a big positive number. So the slope here must be flat because that's a 0 slope. And the slope here must be steep because it's got a slope of 20. Yes, sir?
So would that be exponential?
I don't think it's exponential, but you guys use that phrase to indicate a curved graph. There are lots of graphs that curve upwards. So I'm not trying to say what kind of function this is. I am saying that the velocity does change in a regular and repeated way. Hold on. Right, I notice that the velocity is getting bigger in a regular way. Wouldn't you guys say that? With every second, it adds the same amount of velocity every time. So I want to connect these two dots in such a way for the slope to be low in the beginning and high at the end. Maybe something like that. Some way of connecting it so that it has a shallow slope at the beginning and a steep slope at the top or at the end. Now, you said exponential, and while you guys pack up, let me just point out, exponential means this. But all of these graphs would look like this. Right, they would all slope upwards. So I don't know which one of those it is. Not yet. We'll have to figure that part out. All right, so I walked around the room and basically I saw about 70% compliance. 70% of the people had made a reasonable attempt. Of those, many of you have the correct answer, but a few don't. So I think, go through this with a certain amount of speed. So let me start by identifying where 0 is. I think that's necessary. And I'm going to describe this object a little bit. I see a linear slope. Would you agree? All right. So when I go to find the area, this is the first area that I see. The area bounded by the curve and the horizontal axis. And if I use the definition of triangle, 1/2 base times height, I'll get positive 125 meters. That good? And then I see this side. And, well, I see some symmetry here, but it's all on the bottom of the axis. So this is negative 125 meters. Correct? I see 3 important points here. I say they're important because this is how fast it starts, this is how fast it ends, and in the middle, it appears to stop. Is that all good so far? So if you followed along with what we did yesterday, you probably were pretty successful over here in setting up position, time, perhaps marking the 5-second mark and the 10-second mark. I mean, you could mark more, but this is really what the parts that were important. It started at the origin. After 5 seconds, had moved a positive 125 meters. So there. And after another 5 seconds, it moved a negative 125 meters. So there. Continuing our discussion from yesterday, at the time 0, its velocity was 50 meters per second, which means it had a slope of positive 50 here. At 5 seconds, it was stopped. So it had a slope of 0. And at time 10 seconds, it had a velocity of negative 50 meters per second. So it had a slope of negative 50. I saw some weird graphs out there, but most of you recognize that the object moved in the positive direction, then moved in the negative direction, ended up back where it started. So you had something like this. And how you connected them? Not perfectly symmetrical. I would probably like a little more attention to detail to make it symmetrical, because whatever it did in a uniform and regular way. And so I should see symmetry on both sides. But ultimately, this is what we see. So I saw that on a lot of papers. Do me a favor. Find the acceleration of the object. Can I call you guys out? Just pick on somebody, or do you need more time? These numbers should be pretty easy to work with. You good? All right, Ali, what'd you get for the acceleration? Negative 10 meters per second squared. Acceleration's negative, everybody agree? Line's negative. So was this object speeding up or slowing down? You sure? Are you sure? The object started at 50 meters per second, and in the first 5 seconds slows down to 0. Does it continue to slow down?
It goes back the other way.
I'm thinking that it begins to speed up after that, doesn't it? It's going in the other direction, but it's definitely getting faster, starting from 0 and going up to negative 50 meters per second. The first thing you will have to probably detach in your mind is that acceleration has direction, but that does not tell you whether it's speeding up or slowing down. You'll need context for that. This object has, I think, 4 defining characteristics that you should be able to describe. If you can't, you will not get all the points on the next test. You should be able to tell me whether this object is traveling towards you or away from you. You should be able to tell me if the object is speeding up or slowing down. You should be able to describe the acceleration and describe points of interest. You should be able to do all of that for the time interval that we see. Again, you should be able to tell me whether the object is traveling towards you or away from you, speeding up or slowing down, what the acceleration is of the object, and any points of interest. This object slows down as it travels away from you. Does so for 5 seconds, stops, turns around, and comes back. It has a negative acceleration the whole time. So what does the negative mean here? I'll say it again, the acceleration is a vector. It points in a direction. This object's velocity is becoming more negative all the time. This is a hard concept for some of you, so think about it for a moment. The object started with a velocity of 50 meters per second. Over the entire interval, the object's velocity is becoming more negative. In the first second, it goes from 50 to 45, and 45 to 40, and 40 to 35. It's becoming a more negative number. But it started in the positives, so right now this acceleration is just taking away velocity. Eventually it gets to 0 and continues in the negative direction. Can you think of something you could do that would be like this? Yes, sir?
Throwing a ball up in the air.
Throwing a ball up in the air. I think that's an excellent example. What's the slope of the line as it passes through 0? So it wasn't 0, was it? Does this line have a slope there? Is there a slope right, here at that point? That slope is still -10, isn't it? Something you could do that would be like this. So here you are, and you're going to throw a ball up in the air. Let's say that for the time being, I can't draw it all in one direction, so we'll draw the ball kind of in some snapshots until it comes back down to you. That's good so far? The entire time the ball is moving, we are told the acceleration was negative. Let's put some context in here. We threw the ball away from us with a positive 50 meter per second velocity. That was kind of defining upwards to be positive and downwards to be negative. This is your example, so I'm just using your example, but in your example, you said throw the ball away from you, and I'm trying to mimic the graph, which said we started with a positive velocity. Does that make sense so far? In the next instant, the ball's velocity decreased. In the next instant, it decreased even more. Eventually, there was a moment where the velocity was 0. But after that, the object started traveling downwards. And the velocity increased until eventually it was traveling the same speed it was traveling upwards, but now downwards. Does that make sense so far? Velocity points in a direction. That's easy. The direction something's moving is the direction the velocity points. Acceleration's harder. You can't see it the same way. But we're told that the acceleration is negative, which means the acceleration must be pointing downwards the whole time. Acceleration was negative there. The acceleration is negative here. The acceleration is negative here. In every case, the acceleration was taking away from the velocity, making the velocity a smaller arrow, because the acceleration pointed downwards, but the velocity pointed upwards. What's the acceleration when a ball stopped? So yeah, there's an acceleration here. I know you guys don't like this, and you'll get this wrong in the next test, but when the ball stopped, its acceleration didn't go 0. If that were true, then why would the ball start moving again? Acceleration is the rate of change of velocity. The acceleration is 0, there's no change in velocity. Does the ball come back down? Yeah. The ball does come back down. You throw a ball up in the air, I promise.
Except the acceleration was 0. The acceleration was 0 and it stopped moving.
Okay. I believe I moved past that, but okay.
My bad.
No worries. But I think we can easily imagine that the acceleration had to be pointing down while the ball was coming down, it is at this point that we tend to make a mistake, and I bet I can fool you on the next test. Last year, I fooled about a third of the students just by trying to see if I could catch them in this point. But you tend to make this mistake. When when velocity is 0, that does not mean the acceleration is 0. Yes?
Then what is the acceleration?
What do you mean? In this problem, it was -10. But do you mean like as a definition?
Oh, okay.
Are you sure?
Yeah.
Okay. Now, I'm trying to indicate to you guys that the acceleration has a direction, that it points in a specific direction. In this case, the acceleration was always downwards. What do you think was pulling the ball downwards?
Gravity?
Yeah, do you think gravity stopped just because the ball was in the air?
No.
Do you think gravity stopped because the ball stopped?
No.
No. So the gravity was always pulling on the ball. That was what was causing the ball to come back down. That's what gave the ball this acceleration. That's why it's an excellent example for us to use. So the entire time the ball is in the air, it has a negative acceleration. But don't for a moment think that acceleration necessarily tells you speeding up or slowing down. That part is situational. It depends on what the ball was doing. That will tell you what the acceleration will cause. So I'm going to catch you in a minute. I'm going to give you one that you are going to get wrong. So I want to see if you guys really can apply what we've said. I've given you a ton of information. I've repeated myself several times now. I've given I hope for you visual learners, I've given you a wonderful picture of a kid throwing a ball in the air. And as of tomorrow, you'll start throwing balls in the air yourselves to measure this. So let's do an example. Let's see if I can catch you. I'm going to give you a velocity versus time graph. I'm going to ask a variety of questions. I want to see if you can apply what we've been doing to this situation. And I'm going to tell you from the very beginning, I am trying to trick you. Okay? All right, so this is a picture of what the object is doing. So, same things. Is this object speeding up or slowing down? Is it traveling towards you or away from you? Sketch me a position versus time graph. What's the acceleration? Assume the object begins at the origin. I'm trying to trick you. Let's see if you're tricked. Time equals 0, the object's at 20 meters per second in the negative direction. And over 5 seconds, its velocity becomes 0. It's slowing down. It's moving backwards. The entire displacement's negative, but it's slowing down the whole time. Now, its acceleration, well, that's pretty easy. It's +4. So although it's slowing down, it has a positive acceleration. And if I pick 2 points on the graph, this point and this point, it goes from, let's see, I would say the rise, +20, meters per second, and the run, 5 seconds. Gives me an acceleration of positive 4 meters per second squared. So although it's slowing down, it has a positive acceleration. All right, position versus time graph. So I'd start with a kind of a blank slate here. Saw a lot of interesting things here, most all of them wrong. 5 seconds time, position, meters. I am told to start at the origin, so put my dot there. The area here is 1/2 times negative 20 times 5. So that looks to be negative, let's see, 50 meters. So my displacement over the 5 seconds will be to negative 50 meters. Good so far? My velocity at t equals 0 is negative 20. So I need a slope that is negative and steep. It's amazing how many of you have your slope there flat. It's like 3/4 of the class who did this. That's not what this is. It says it starts at a velocity of negative 20 and ends at a velocity of 0. The only way I can connect these with a smooth curve would be something like that. You guys are going to be easy to fool tomorrow. And I am saying tomorrow because we're going to try this tomorrow. I think that's not an unreasonable request. First few minutes of class, put a couple of these on the board, ask you guys to give them a try. Want to try another one?
Yep.
All right. I'm going to stick with not making you do too much. All right, so acceleration's negative 3 meters per second squared. Feel good about that one? So our acceleration's negative. Is this object speeding up or slowing down?
Slowing down.
See, it starts at 12 meters per second. And then after 4 seconds, how fast is it going?
Stops at 0.
0's okay. So I'd say it's slowing down. Yeah. During that time, looks like it travels, what, 24 meters? That's the area I see in here. So if I was to come up with a position graph, assuming it started at the origin, after 4 seconds, position would be over here someplace. the slope at time equals 0 is positive. It's positive 12. So I would have a positive slope here. And the slope at the 4-second mark is 0. So the slope at the end would be this. A smooth curve that would connect those two things together. Something like that. This is the first half of the one I just did on the worksheet. I'm not trying to trick you. And if you're being tricked, do you notice I'm doing the same kind of procedure each time? You could probably come up with a set of rules to govern speeding up and slowing down. Like, if the acceleration is negative and your velocity starts positive, then it's slowing down. If the acceleration's negative and the velocity is already negative, then it's speeding up. You could probably come up with a set of rules. I'll let you reason that kind of thing out if you need that for your own notes, but I would prefer you be able to reason that out on your own. I want to step up the level of difficulty because this is not the level I wish for you to be working at. I want you to be better. And so I'm going to step it up, but note that I'm not stepping it up very much. I want to add something that I have not talked about yet. How far does this object go? What's the displacement of this object? I want its acceleration too. But what's the displacement? I've been kind enough to give you rectangles and triangles. This is neither of those, and you should know what this is. And somebody put their hand up, so I'm glad, but I think you can do it. I want you to tell me what this shape is, and how would you find its area? And if you break it up into two pieces, you're doing it wrong. You've had geometry. You know what this shape is. I think I'm sad. I don't think you guys know what the shape is. How many of you recognize this shape? Yes, ma'am. What is it? Either one. It is a trapezoid. That's right. I have two parallel lines and two other sides. That makes it a trapezoid. Do you remember how to find the area of a trapezoid?
Yeah, the height times like the side and then like the base, and then you divide it by 2.
That's right. It's 1/2 times the sum of the bases. times the height. So you have a trapezoid. A triangle is a trapezoid where one base is 0. So it's also just the average of the two sides. So in this case, 30 meters. Right? 15 plus 5, 20. Half of 20 is 10 times 3, 15. I'm sorry, 30. So positive 30 meters. Acceleration, positive 10/3 meters per second squared. So a trapezoid shouldn't throw you, right? Continue at this level of difficulty. I have high expectations because these problems we're doing right now are your homework questions. If you've actually tried the homework, this is the kind of stuff I'm asking for in the homework. Same question? Look, there are 2 minutes left. How many of you are breaking this up into two areas? Two triangles? I want you to stop. I want you to pay very close attention. This is a trapezoid. I know it doesn't look like it. In non-Euclidean geometry, you can have the sides overlap. Imagine a sunshade that you flipped. You guys know what I'm talking about? One of those ones you fold? I've taken the same trapezoid, same sides, and flipped it around. Use that and figure out the area instead. 1/2 base 1 plus base 2 times the height. Okay? It's -5 times 3, it's -15. I'm sorry, it's +5 times 3 is +15. Half of 15 is 7.5 meters. If you find the two areas and add them, you'll get the same answer. You should try that. But I need you to see that this is still a trapezoid. Yes, ma'am?
Oh, I was just gonna ask, like, why wouldn't you just do the triangles?
There's something we're going to do tomorrow that's going to transcend this, and we need to have seen this. So I would encourage you to do the two triangles and add them together. You'll need to figure out where this point is to do that. Not too hard on this example, by the way. I did it on purpose. That point's at 1 second. But I want you to understand I don't have to do that. So there's some purpose here. Please, do what I've just asked. Try the two different areas. Show that they equal this. All right. Tomorrow, we are going to extend this. You should practice the homework I've given you. The one that says, has a picture of a velocity graph and gives you a situation and asks for some answers.
This one?
You should try it. Perhaps we could start here and maybe talk about a few of the things that we discussed the other day. Some points that might be of use in looking at what you are supposed to do with the information presented. Now, let me be really clear. There's a variety of things I can list here. I'm only going to list the stuff that we already talked about. So, for example, a position versus time graph. We talked about that in this, with some reflection on the two cyclist problem. We had cyclist A and cyclist B. And in discussing that question, we came up with a couple of straightforward pieces of information. First, position graphs tell you where the object is. I know that sounds silly, but trust me when I say you need to be able to tell me what the use of a position graph is. So it tells you where the object is. You may be able to get other pieces away from it, but that's what a position graph does. It tells you where the object is. You told me, I didn't tell you, but you told me that the slope I helped you with the vocabulary, but you were able to come to the conclusion that the slope of this graph was how fast the object was traveling. I put a vocabulary word to it because it not only told us how fast the object was traveling, but depending on whether the slope was positive or negative, also indicated in what direction the object was traveling. So that's why the word velocity is used here. And that's it. That's the extent of what we came up with. There are other things we can get from a position graph, but that's the extent of what we discussed the other day. We also discussed the velocity versus time graph. And I think, again, what does it tell us? Well, first, it tells us how fast and in what direction the object was traveling. That's what it tells us. How fast and in what direction the object was traveling. I'm really careful about this next part because it does not tell us where the object is. It doesn't contain that information. It does not tell us where the object is. It can't give us any positions. But we did determine something about the graph that we could use. It can tell us the change in the object's position. So it can't tell us where the object is, but it can tell us how far the object moved. So, and that's the area. Bless you. The word that we use here is displacement, which is the word I used in class. The area can tell us the displacement of the object. Displacement is defined as change in position. There are students in this room who don't understand what I'm about to say, and that's okay. Write it down anyways. You're going to need to come to understand it. Knowing an object's change in position does not tell you its position. So you need to be aware of that. That's different. We need a point of reference if we want to know the object's location. And it was given to you. It's at the top of the worksheet. It tells you to begin the object at the origin. So it's telling you where the starting position is. But the graph can't tell you that. Now there's more information to put in this chart. This is just to get us started, but this is all you need to do what that we have here all still apply. None of these rules are different. For example, on a position versus time graph, the slope is the velocity.